So as Michal introduced, I'm the JSR 277 specification lead, and Michal is also one of the contributing members in the 277 expert group. And this afternoon, we are going to present the Java module system. So let's get started. So here is the goal of this talk. But what I would really like to talk about first is what exactly are the problems we are trying to solve with the Java module system. If we look at the Java SE platform today, the common standard packaging format is what we call the Java archive or the jar file. It was first chosen by Netscape as a way to package classes and resources in Java applet in the browser back in the 1990s. And later, it was adopted by Sun in the JDK as the standard packaging format in the Java platform. If we look back, the decisions was rather arbitrarily. It was not because there are a lot of advantage of the jar file format. It was mainly because of the popularities back in that time. But the decisions has worked reasonably well, and basically, every applications right now make use of the jar files. But as developers use more and more of the jar format in the last 10 years, it also shows its deficiencies. For example, it is rather difficult to express versions information in the jar files. And if you want to express version dependencies between two jar files, there's no easy way to achieve that. And if we look at many Java applications today, it consists of not only one jar, but multiple jars, and sometimes even native libraries. However, there is no standard packaging format to group them all together and distribute them as one unit. And as a result, many developers are either being forced to zip up everything and distribute their applications as a giant zip file and hope that the end user will be intelligent enough to unzip it and deploy it properly. Or they may be forced to create a custom native installer to bundle their applications together for deployment and distributions. Further, if we look at how the jar file format is being used in the JVM, it also serves two different roles. On one hand, the jar file is a distribution format. On the other hand, the jar file is also being used as an execution format in the JVM. So one of the implications is that whenever you try to start up a Java application, the JVM has no choice but to scan all the contents in the jar files in your class path one by one. The reason for that is because there is no metadata in all these jar files to tell the JVM what it contains. And it has significant performance impact to every Java applications out there. So all these deficiencies can be summarized in what I call three kinds of hell: the class path hell, the jar hell, and the extension hell. I'm not going to go into details here because I can talk about it all day. But there are basically various problems related to class loading, packaging, and deployment in the Java platform that every Java developer would have encountered. So the goal of the Java module system, or JSR 277, is to produce a module system that addresses all these deficiencies and more. The Java module system is targeted for the next versions of the Java SE platform. It will provide first-class modularity, packaging, and deployment support that is built into the platform. There will be a new versioning scheme that allows developers to express versions in a module, as well as versions dependencies between the modules. We'll also have a new distribution format, which is what we call a gem file, that enables developers to package not only classes and resources, but also jar files and native libraries together as a unit of distributions. The new gem files will also contain metadata, which has all the modules information in it, and this makes it easy for discovery, and it also makes the module self-describing. And in order to deploy such a modules, we will define a set of repository infrastructures that enables developers and deployers to put multiple versions of the modules on the same system side by side. So different applications can pull different versions of the modules they like from the same repository without any conflicts. And all these modules will be installed in the repository in isolations. And all this will be supported by a comprehensive runtime that will be defined by the module system. Now, in order to make the module system easier to use, we would like to integrate the development as well as the deployment experience with the language and the JVM through JSR 294. So for those of you who are not familiar with JSR 294, it is a JSR that will define the linguistic unit of modularities in the Java programming language. And it also deals with the problems of information hiding and separate compilations. So going forward, developers will be able to write a module directly in the Java programming language, compile it, and turn it and package all the classes and resources, etc., together into a deployment unit that can be used by the module system. We would also like to integrate the module system with the classes libraries in the Java SE platform, as well as the JDK tools. So in the future, you will be able to leverage the functionalities and features in the module system transparently from your program when you make API call and things like that in the Java SE platform. We also plan to make a set of reflective APIs available for programmers to use. What that means is that all the key abstractions in the module system, such as modules, modules definitions, repository, etc., they will all surface at the API level. So you will be able to make use of those APIs to build something very powerful in your program. The architectures of the module system is also designed to be pluggable and extensible. So let me explain this a little bit. What this means is that third parties may provide their own custom repository implementations using whatever backend or underlying storage model they like and plug that into the module system for it to be used. So third parties can add values to the module system this way. And also, the architecture is extensible. So some of the existing module systems, such as NetBeans, OSGI, etc., they can also plug into this framework and expose their modules directly as a JSR 277 modules for interoperabilities. And I'll talk about this later. And obviously, there are many existing systems out there that are solving something similar to what we are trying to do. For example, .NET, OSGI, NetBeans, Maven, Ivy, etc. So in order to learn from the experience of all these existing systems, we have a fairly large expert group, which currently consists of 20 people from various companies and developers in the industry. So we hope that we can draw from their experience so we can build a better module system. Now, let's go into more details a little bit. But before we get there, so let me try to clarify two distinct concepts when we talk about modules. On one hand, there is a concept of modules for development. On the other hand, there's also a concept of modules for deployment. So let's talk about modules for development, or the development module first. So the development modules is basically a unit of linguistic modularities. And developers would typically write such a modules using the new super package construct that will be defined in JSR 294. And when you compile it and try to load such a modules into the JVM will make use of the information in the development modules to enforce the modules level access control. On the other hand, deployment modules is very different. As its name indicates, it is all about deployment. It is a unit of reuse, versioning, and packaging. And it also consists of metadata, which makes the module self-describing. And in order to deploy such a modules, you will use the repository infrastructure in the module system. So potentially, you can make use of this infrastructure for site-by-site deployment. And there will also be extensive tools and library support for the deployment modules. So you may ask, what exactly is the relationship between a development modules and a deployment modules? So developers would typically write the modules using the new super package construct, and they will compile it and turn it into various kinds of artifacts. And one of the artifacts is the metadata for the deployment modules. So developers can simply package the metadata along with the classes, resources, and other things together into a deployment modules for distributions. Now let's look at an example of what a development modules looks like. So in this case, I have a com.sun.myModules that is declared using the new super package construct. And inside modules, it is typical to have public API as well as implementation classes. And both of them belong to the modules as the members. So I could use the member package keyword to declare what exactly are the classes that belongs to be part of the modules membership. And even I have the public API and the implementation classes, developers normally only want the public APIs to be visible and accessible outside the modules. And to do that, you can use the export mechanisms to specify in the construct. And it is also not uncommon to have modules that depends on other modules. And to express such a dependency, you could use the import mechanisms to declare it in the construct as well. And notice that the import in the example is currently being highlighted. And the reason for that is because the import mechanism is currently not defined in the JSR 294 specifications right now. And this is something that we will still need to sort it out with the expert group. Now, if you look at the modules information that is specified in the super package construct, it has the module's name, the membership, export, import, etc. I mean, they are pretty simple and easy to specify. But what happens if I want to specify something like the versions of the modules or the resources that I would like to make visible and accessible from the module class loader, etc. Now, to do that, JSR 277 will provide a set of annotations for developers to use. So you could use something like @versions to specify the versions of the modules with the super package, or you could use the @export resources annotations to specify the resources that you would like to make visible or accessible from the module class loader, etc. So one question you may have is that, so how come some of the modules information is specified directly in the language construct, while some of the other information are specified using the annotations? Now, the quick answer is that all the information that is specified in the super package construct, they must carry semantic meaning in the language and understood by the compiler at build time as well as by the JVM at runtime. While the information specified in the annotations, they carry no semantic meaning. Okay, so once we have specified all the modules information in the super package construct, maybe in the form of annotations, maybe directly in the construct itself, what happens if I compile such a super package? The result is that there are two kinds of artifacts. On one hand, the first kind of the artifacts is what we call the .superpackage files. The .superpackage files is the authoritative binary definitions of the modules. It consists of the module's name, modules, export membership, import, etc. And at runtime, the JVM will make use of the membership and the export information to enforce the access control. And this file can also be used as the metadata in the deployment modules. The second kind of the artifact is what we are familiar, which is the .class file. Now, if you take a Java class that belongs to a super package and compile it, the result will be a .class file, except that in this .class file, it will have some special attribute which indicate which modules it belongs. And when such a .class file is being loaded by the JVM will look at the attributes in the .class file and cross-check the membership information in the .superpackage files. And this is done for obvious security reasons. Now, if we look at the entire development models and step back a little bit, what we are trying to do here is to enable a ease of use experience for development and deployment. Developers would typically start writing their modules using the super package construct, and all the modules information will be specified all in one single source file. Then they can compile it, and it will automatically generate some artifacts which can be used as the metadata of deployment. So every time when you try to make use of, or when you try to update the modules information in the super package files, all you need to do is simply recompile, and the metadata will be automatically synced up. And this model also makes it possible for tools to combine the compilation as well as the packaging into one step. So some tools can take a super package source file along with the Java classes, compile it, package it all in one step, and turn it into a deployment modules for actual distributions. Now let's look at what a Java module looks like at the logical level. So in the modules, it has the metadata, which consists of the module's name, etc. And this is what makes the module self-describing. It also has the classes and resources that are part of the modules. And in addition to that, the modules can also have jar files embedded in it, as well as native libraries. So if you look at some of the standard extensions today, such as Java 3D, they consist of multiple jar files and native libraries. And the way we currently distribute it is to deliver them as a native installer for installations. And going forward, this kind of standard package, standard extensions can be packaged together in one single Java module. And this makes software much more easy to distribute and deploy it. Now let's look at some of the information in the module's metadata in more details. So each module consists of a module's name, which has 5 different parts: the major number, the minor number, the micro number, the update number, as well as a qualifier string. And developers are expected to increment or change each of the parts depending on the degree of changes that they are making in their software. And in case there's no versions numbers declared in the modules, the module system will automatically provide a default versions for you. Now, as I said, a module typically consists of public API as well as implementation classes. Now, to make the public API accessible and visible outside the modules, you could use the export mechanisms. And there are 2 notions of export that we support in the module system. The first notion is export classes. And to declare that, you could simply use the export keyword in the super package construct. And this will be recognized and supported by the compiler as well as by the JVM at runtime. So when you try to compile certain classes that are modules private in some other modules, the compiler can make use of the export information and catch these kinds of errors. Now, the second notion of export is what we call export resources. So export resources are the resources that are visible and accessible when you call a certain method in the module class loader, such as get resource as stream, or get resources. And they can be declared using the @export resources annotations that can be attached with the super package construct. Now, we have just talked about export. So how about import? Now, import is the mechanism that allows developers to express dependencies between modules. And the dependency is basically expressed using a module name. So in the first example, the XML modules simply import the SOAP modules. And at runtime, the module system would interpret it as importing the highest versions of the SOAP modules available from the repository. So what happens if I don't want the highest versions? And in this case, you can express it in the second example using the @versions constraint by specifying the versioning requirements that you want, and the module system will be able to honor that. And the import can also be made optional, as well as in some cases, you may also want to re-export the imported modules from your modules as well. And they are all supported by the module system.
I have a question. On the previous slide, re-export. Why is that an annotation? Does it have no semantic effect?
At this point, yes. Currently, it does not have semantic meaning. But this is something that we're still working on with the expert group to find that out. Yeah, so why is the re-export carry no semantic meaning? Yeah, and as I said, this is currently just what we have defined in the 277 specifications, and this is something that we will still need to work with the 294 expert group to figure out what the right semantic meaning should be in the language. Okay. Now, I've just talked about how you would write a module using the super package construct and generate it and turn it into some module's metadata. And once you have that, then you can package the metadata along with classes, resources, maybe even jar files or native libraries, and group them together into a distribution format for actual deployment. Now, the module system defined a distribution format, which is what we call the gem files. The gem file is basically based on the popular jar file format, except that it has metadata as well as it has the abilities to carry jar files and native libraries. And because the format is based on the jar format, the gem files can be digitally signed using jar signers, as well as verified in similar way. It can also be further compressed with PAC200. So I don't know how many of you are familiar with PAC200, but it is a hyper-compression technology defined in JSR 200 that will give you a very high compression ratio, such as 1:8 or 1:9 compression rate. And this will make the size of the gem files much smaller and make it easier for distributions on the web. And the module system will have built-in support for PAC200. So if you have a packed gem files provided to the module system will be able to automatically unpack and deploy it for you. Now let's look at an example of what a gem files looks like. In this case, I have a alt.full.xml modules with version 1.2.3. And as the file name indicates, the module's name and the module's versions are all part of the file naming conventions of the gem files. And these files also end with the .gem extensions. Now, if we look at the content of the gem files, you may find something more interesting. In the first entry, I have the manifest.mf. Well, no surprise, it is typical in any jar files. In the second entry, it is more interesting. The entry is the modules.metadata. This is the files that gets generated when you compile the .super package. And this is also the metadata that makes the entire gem file self-describing. And inside the gem files, as you can see in the next few entries, I could also put native libraries and jar files, and they're all being stored in some special locations. And for the rest of the classes and resources, they are simply stored at the root of the gem file, which is similar to how classes and resources are being stored in the jar format today. Now, once you have packaged everything together as a gem file, you can now distribute it to other systems and deploy it. And the way to do that is through the repository mechanisms. And I'm now handing over to Miham to talk about that.
Thank you, Stanley. You already heard from Stanley the rationale and motivation for having repositories. But let me just quickly recap what are the benefits of this new mechanism. So a repository is the black box implementation of how modules are stored on a system. And they basically follow a standard API developed by the module system. And there are multiple benefits of this. First of all, you can store multiple versions of the same module in a repository or across multiple repositories. And you can implement an algorithm that I'll describe later that basically chooses which of the versions is being used to satisfy which import. But furthermore, this is a mechanism that we will use to make it possible for other module systems to be plugged into the JSR 277 module system. So one might imagine a repository that helps the NetBeans or OSGI module systems be implemented and deployed side by side with the rest of the module system. But another benefit that hasn't been mentioned yet is that because the implementation is a black box, you can imagine whatever optimizations and implementation of actual storage as you wish. So you could have some database backend or whatever you want that can be just a custom implementation of a repository. And all this will be supported by the module system. So with all this flexibility, you might already imagine that there will be multiple repositories present on the system at the same time. And some of them, of course, we cannot even envision exactly what they would be. But let me give you a few examples of those that we already know will probably be present on many systems. And I will describe roughly the differences between them. So the Bootstrap repository is the first one that you will see everywhere. This is the most privileged repository that contains all the core packages from the Java SE platform. So any package that starts with Java has to be stored in this repository. It is not considered secure to store it in another repository. There will be multiple kinds of global repositories. We envision, for example, there could be one system-wide global repository that would be under control of the administrator, in which some modules can be stored and can be used by various users. It can be also a global per-user repository that can be used by multiple applications of the same user only, and no other users will be impacted. An application repository is the one that will be created automatically by the system if you want to quickly deploy an application that wasn't actually installed in any of the repositories. It will be created on the fly at application startup, and it will have all the right properties of repositories. The last two kinds you can see on my slide, the local and URL repositories are a little bit different than the previous ones in the sense that they make it easier to share and to deploy modules. In the local repository, you can basically drop a module file into some chosen directory. It's called the module interchange directory, and it will just be picked up from there. So what follows is that, first of all, of course, it's easier to deploy, but also some optimizations that are possible because you know exactly what is installed will not be so easy to do in this repository. This is also the one that can be used to share modules across multiple JREs that you may have implemented on your system, because there's one single directory that will be basically specified as the base of this repository. A URL repository is similar, but it's further optimized for network downloads that may potentially go over low bandwidth connections. And there will be a way to quickly get the metadata without downloading the whole jump file. Enough of the metadata to resolve the imports and to reason about what is actually in the module. So all this leads me to this optimization bullet at the bottom. We don't know exactly what will be implemented, but given this mechanism, you can imagine that many operations that are today performed at runtime can be actually done earlier. So anything from, say, class verification to indexing all the files, or maybe even to native code generation can be done early because there's a single point in time when modules are installed and uninstalled, and the whole system can reason about it. And it's hard to say what exactly will be supported by which JREs, but at least there's the freedom to make it possible that it's not quite there today with that standard class path search mechanism. So with all those repositories, you of course probably have already guessed that there's some way to connect them at runtime. And if you are familiar with Java class loaders, it is somewhat similar to this. There's a delegation process going on. So there's always some repository in which you start your search for modules. And if this repository has a parent repository, it queries the parent first to find out if there are some other modules present there, and somehow the combined set of all modules is being taken into account. To explain how this works, I will take this more general picture. We see here some repositories connected into this diagram. Let's make it simpler and take a specific example. So imagine a simple application that has a global repository as a parent, and this one has a bootstrap repository as a parent. And let us imagine that in this application, there are two modules, the application module A and some library module B. And they have those two versions, 1.0 for both of them that you can see. Now, further imagine, to make it interesting, that there are more versions of the B module installed on the system. So you can see some other versions, 1.4 and 2.0. And now the question is, if A imports B, which version of B would be imported, and what the mechanism for this is. So this is what the example will illustrate. So imagine that module A that we want to resolve its imports for has the following version constraint. You have seen already in an earlier slide a simpler version constraint. There's a specific version. Here you see a range of versions that is the constraint. If you look carefully, you see that there's a square bracket on the left and the round parenthesis on the right, which is supposed to be similar to the standard mathematical notation. So the left range is inclusive in this example, the right end is not. So it means that any module B of version 1.0 inclusive to 2.0 not inclusive would be a valid input for module A, as specified by module A. So there are a few of those in the system that satisfy this constraint, right? So what would actually happen? Because A comes from the local application repository, that repository will be queried to resolve the import. And it would delegate it to its parent, which would delegate it to its parent, and the bootstrap repository will look at what it contains and will return the highest version that meets the version constraint, which in this case is 1.4, because 2.0 is too high, doesn't meet the right end. So the 1.4 is passed down to the global repository, which looks at what it contains itself, and finds now the highest version between what it saw in the parent and what it has itself. In this example, you see that actually the same version number, 1.4. So the module system would enforce the property that is important to us, that it's always the case that parent is trusted at least as much as the given repository. So there's always a preference given to modules loaded from the parent. So in this case, the 1.4 from the bootstrap repository will be the one returned by the global repository. So now this will be compared with what's in the application repository. There is no higher version there. So the version 1.4 is the one that will be used and as the import here. So it's a pretty simple example, but it explained a few concepts here. Now, whenever we talk about import mechanisms, sooner or later, someone will ask us what happens in a case like this. And someone will always draw a diagram kind of like this. So let me explain what the problem here is. Imagine we have some module A in this example, that has two imports, B and C, two modules, and both B and C import the same module D. So what people would like to see is that the same version of D would be wired to both modules B and module C. And this is a desirable property. So to understand, to navigate the graph, let me explain, give a little bit legend to what's there. So every node in the graph is a module, is a version, and name for it. Every edge is a version, is an import, a dependency, and the label next to an edge is the version constraint. So you will see actually a new syntax here that I haven't shown before. Import from A to C is basically with a plus sign. It means it's version 0 or higher, which specifically means any version, because every version has to be at least version 0. So in this example, we see this sharing, and this has multiple benefits. The first one is performance. If you have only one copy of every module that is ever referenced, of course, there's less of a memory footprint, and this is a good thing. But it's also correctness. If any of the public APIs of B and C use classes from module D, if you have different versions, there will be actually a mismatch. So if, say, a method from module B would return something of some class from module D, they were supposed to be passed into module C, but there were different versions. There will be a class exception that would basically fail at runtime. So those are the two reasons why you would like module sharing. Now, why would you ever not get the module sharing? So this is what the next slide illustrates. If the version constraints for all the imports of module D all of the graph for the application were different, you might end up in a situation like here, where module B cannot use the version 1.1 because it's too high for its version constraint. But for module C, this is the highest compatible version, so it can indeed use this one, and we have two different versions that are used here. So what can you do? Clearly, the person who wrote the code and created the module cannot do much about it because B and C can be deployed by someone else potentially. It's completely to be outside of their control. So there's nothing you can do. But once you have deployed everything in the system, there are some things you can do because you know all the repositories, you know the content, and you can tweak somehow how the inputs are being resolved. And this will lead me to the next slide, which shows some advanced features of how we can control what inputs are being provided. So the first feature is a custom import policy. This is actually embedded inside the module, and it gives you more power than a standard version control. It's actually a piece of code as a class that follows some standard API that has been invoked by the module system to find out which versions of modules satisfy a particular import. So this is a fairly powerful mechanism. It would be best if it was never used, because of course it's better to use declarative approach in general than imperative. But in some cases, for example, for different module systems, it may actually be required to provide more functionality. Now, the other two mechanisms, the override mechanisms, are the ones that can be actually applied to solve the problem from the previous slide. So let me describe them briefly first, and then I will show you the graph again and show you how they address the problem. The visibility policy can be applied to a given system to determine which modules are visible for any resolution action that ever happens, and which are not visible. And the import override policy is specifically targets a particular one import. So it is consulted whenever an import is resolved, and it can say something like, if this class imports the other class, I actually want to narrow down the constraint to only use some versions rather than the more wide constraint of the original specification. So let me go one by one, start with visibility policy. So imagine the same graph. We have this unfortunate situation that there is no sharing of module D, and we would like to fix it. So the visibility policy would let me look at the situation and say, well, I know that the problem here is that module D version 1.1 is visible. I would like to admit it's just not visible. So you install this visibility policy that this is what it does. Makes it invisible. And therefore, now if now you look at the version constraint for import from C to D, there's only one version that satisfies it, which happens to be the same as the one from module B. So you get to the same sharing problem.
Who makes it invisible?
The administrator, for example, or maybe the user.
So it's none of the modules makes it invisible.
Yeah. So let me repeat the question. The question was who makes it invisible? So none of the modules make it. So there was the other mechanism I mentioned earlier, the custom import policy that could do this. But we generally would discourage people from doing this because the other modules that you see in a system are not necessarily yours. So say in this example that A, B, and C are deployed by different people. So you wrote A, and I wrote B, someone else wrote C. You have no control over the imports of C. So there's no way for you to influence this. Only the end user, the administrator, has all the pieces at the same time and can make this decision. But if you wanted to, if someone wanted to guess, you could write a custom policy that says, oh, it happens to be Mihaw's version of B, then do this and modify the constraint. You could do this if you wanted to, but don't believe that this would be a right thing to do.
What if the user is not intelligent enough to make this decision?
So the question is, what if the user is not intelligent enough to make this mechanism work? And of course, this is an inherently hard problem. So I have to say that there's no magic bullet. We're dealing with an extremely complex system. Somehow determines all these versions incompatible. It has to be a highly skilled person. So unfortunately, we don't solve the problem of people who don't know how to do it. No, there's no solution for this. So the next mechanism is this import override, which is a little bit different in the sense that module D version 1.1 is still visible in the system for some other applications, perhaps, that want to use it. But we know that this particular application cannot deal with this. So we just attack this one import from module C to D, and this override says, well, let's narrow down the version constraint so that now it's 1.0 to 1.1, and therefore will not use 1.1, even though it is still visible for other applications. And it has the same property as before. It's only for advanced users, but this is why my slide was called advanced mechanisms. We don't anticipate that an average user would be able to use this. But there are very complex systems in practice that people do demand this kind of power, and we had specific requests from some companies that would like to have this ability, and they basically couldn't live without some mechanism like this. So it is provided. It is provided by many other module systems as well, some way of overriding what's in the module system, and it has been used in practice often. Do you have a follow-up question?
Well, the way you've defined it, it makes it impossible for a module to ever rely on version above 1.0 of another module. And this problem keeps coming up every 5 years.
Yeah, so it's an inherent hard problem. So I don't think we claim that this somehow solves everything. But so what specifically would you suggest?
It really doesn't solve anything.
No, it does solve the whole situation. Assume that you are a consultant, highly paid person who would like to fix an application that doesn't work on some system. Now you have a mechanism to make it happen. You just you learn how to write those policies, and you can write them and deploy them and make the application work. There's some standardized way of doing this. And I'm not saying that it's easy, but at least it is possible.
Look at it from a point of view of the person who writes module C. A new version, let's say 1.2 of module D comes out.
Right.
Module C wants to use 1.2 of D, but he can never use it because
yeah, that's true. Right.
If he relies on 1.2 of D, then he'll get the duplication of some poor user's machine who also has D.
No,
and it's saying that, okay, the user's not going to hire a consultant to fix it for them.
No. So the question, to repeat for people who don't hear the question, is that if the person who wrote module C would actually like to use a higher version of module D, say 1.2, that it becomes available, there's no way here to use it. So my answer to this is that in this particular scheme, that is true. But there are ways to solve it. So for example, module B could be deployed with a higher version that can handle higher versions of D, or some such thing could happen.
C has no
yeah, that's absolutely true. That is true. But I don't think it's a way to solve it. Maybe it should, because I kind of tight on time. Let's maybe take it offline and discuss it more. But I admit that we have not solved all. We don't provide a solution that would make some magic happen. This is an inherently hard problem. If you have some, by the way, suggestions how to fix it, we're still probably open to changes. We would love to hear them. So now briefly about lifecycle. So there are two kinds of lifecycle I would like to mention in this talk. One's for repositories. It's very simple. You can initialize one, and then you can shut it down. And there's support for this. We define what happens when you shut down the repository, and some of its modules are in use, and it's all defined. And then for modules, what happens for modules? So the modules have to be first found as this resolution process. This is what I described in the previous slides. How you decide which version is being used for an import. After resolution happens, there's this process called validation. There are actually two types of validations that we define, the shallow and deep one. The shallow one is always run, and it's required for correctness. And all it looks at is the metadata of the module. And it looks whether there is, for every module, looking at all its imports, if there's exactly one class provided for every class that is required by this module. If it's either 0 or more than 1, then there's an error, and you cannot use the particular import. Deep validation does more checks, and I don't want to go into details, but it's expensive enough that we anticipate it will be used for debugging only, not in a normal use. Then, if everything is all right, module is in the ready state, and it can go into error state, as you can imagine, if something goes wrong on the way. So now at runtime, what happens at runtime? So typically, you would see a one-to-one correspondence in the implementation between a module and a class loader. This is needed to have basically separate namespaces in a way for classes of the same name otherwise. And you see here some graph of class loaders, how they're connected. And if you have used class loaders in the past, you probably would see something wrong here, because in today's model, there is no way to have cycles in the class loader delegation system. But we'll leverage the new support for class loaders that will be available in Java 7. And we do require this for modules, because modules do have cyclic dependencies. And the shallow validation I mentioned in the previous slide is actually key to making this work, because we know that for every import, we already validated it. There's exactly one class provided by one of the imports that satisfies this particular reference. We know that this will always resolve in a finite time, and it can be implemented relatively efficiently. So this is about what we thought of to ease migration from legacy systems into the new module world. There are two special modules that are automatically being created by the system. Sorry, not automatically, maybe it's the wrong word, but Java, it can be expected to always exist. Java.se is the module that contains all the existing core SE packages. And it's a single module that is imported by default by every application. So if you don't change a single line of code in an application, you will still see everything you were able to see in the past. It is, by the way, we do anticipate that the SE core platform will be further modularized into finer-grained modules, and there will be a way to rely only on a subset of SE. But if you don't do anything specific, you will import this big module that potentially imports many smaller ones and re-export all of them. So you will see all of the SE platform.
You don't really need all the public ones, like the sun.misc stuff shouldn't be exported.
They probably would for compatibility, right? But in the long, so the question was, would you see things like from Chrome.sun and this kind of stuff? And probably initially they would. And the long-term path would like to maybe get away from this. And the other module is the Java class path module, which is automatically created, and everything that's on the class path at the time of the application start will be automatically added to this module. So again, without having to do anything special, if you just want to access legacy code easily, you can do it via this mechanism. So this concludes the main part of the talk, and I will now let Stanley finish by saying what's the current status and make a few final comments.
Okay. Okay, so I hope we have provided enough information for you to understand the high level of the Java module system. So what is the current status of JSR 277? The early draft review have already been published, and it is available today. If you're interested, you can go to the JCP website to download it. And since it has been published, we have received many valuable feedback from people in the Java communities. So we have been working on the revised specifications in the expert group, and it is currently under review and discussions inside the expert group mailing list. And we hope that we will be able to make these versions of the specification available later this year. Now, one issues that we are going to tackle in the next few months in the expert group is the issues around interoperabilities with JSR 291 or OSGI. The goal here is to provide some kinds of interoperabilities to allow JSR 277 modules to make effective use of the OSGI modules or vice versa. However, the design and the constraint in JSR 277, the Java module system, as well as the JSR 291, the OSGI module system, they are different. So what we are trying to achieve here is not perfect interoperability, but we would like to achieve a degree of interoperability with minimum restrictions.
What is OSGI?
OSGI is a modularity framework defined by the OSGI Alliance, and it currently also runs on the Java platforms.
So just another module?
Yes. Okay. So how exactly do we get there in terms of interoperability solutions? So we plan to develop an interoperability proposals in the JSR 277 expert group in the next few months. Then we will throw that proposals to the 291 expert group for review and discussions. And there are many implementation options currently under considerations, and we are still exploring all the options that we have. So in summary, JSR 277 aims to address various problems in the Java platforms today, including packaging problem, deployment problem, modularity problem, and it will produce a module system that will address all these issues in the next generations of the Java SE platform. It will provide first-class modularity, packaging, and deployment support that are built into the underlying platforms. And it will also provide a seamless end-to-end development and deployment experience by integrating it with the language and the VM through JSR 294, which is the super package JSR. We also plan to integrate seamlessly with the classes libraries in the existing platforms and the JDK tools, so you can make use of the features and functionalities in the module system transparently in your applications. And we are also trying to design the architectures to be pluggable and extensible, so third parties can provide their own custom repository implementations on top of the modules system to add values. Or other existing module systems such as NetBeans, OSGI, etc. They can also plug into this framework to expose their modules as a JSR 277 modules for interoperabilities. And hopefully, the class path hell, the jar hell, and the extension hell will finally go away. And if you are interested in more information, you can check out the early draft specifications. It is currently available on JCP website. One thing to notice is that all the contents that we cover today in these presentations is based on the revised specifications that is not currently available. So when you check out the early draft specifications, you may see a huge difference between them, just to give you a heads up. And if you're interested in observing the expert group discussions, you can subscribe to the mailing list. And if you are interested in the super package, language JSR, there is currently a strawman proposal available that you can check it out, and you can also be a subscriber to the EG mailing list as well. And lastly, at Java 1, 1 or 2 weeks ago, Sun has announced that we will make the reference implementations of JSR 277 as well as JSR 294 available in open source form later this year. And we have currently set up a project on the OpenJDK website, and the source code will be available in the next few months. So if you're interested, you can keep track of all the status and changes from the OpenJDK project.
Why did you not simply intersect the version constraints and pick that one?
Can you repeat questions?
Why don't you not intersect the version
you mean at the language level?
What?
Yeah, are you asking at the language level?
And when this module discovery, you have version constraints.
Yes.
Right.
Why didn't you simply intersect all of the constraints on a particular module and pick one that fell within that intersection?
So the whole API, you're talking about repositories where I showed this delegation module, right?
Yeah.
So the question is, why wouldn't you use a simpler mechanism that simply performs the intersection of all restrictions in all the repositories everywhere? We still have to know which ones are connected in the delegation module. So you just somehow create a list of them, I guess, and do an intersection there, right? In a way, this is what happens. So there are two parts of the system. There's the module system itself, which makes the decisions, the delegations. Each module that provides an implementation that is by someone else, potentially, it only returns what it contains itself. And then the module itself that performs basically an intersection. I described it in a sequential way because this is easier for me to describe. But basically, this is what's going on. Every module says, this is what I have, what matches the constraint. And then some module framework that's part of the JRE performs an intersection, basically, and picks the highest version. Intersection, no, a union, I guess, sorry. A union. Intersection wouldn't make sense. I'm not sure why you mentioned intersection. You really made a union, right?
No, I meant an intersection.
Of all the modules that are...
Right, because you had this example, and 1.0 was in the intersection of all of the constraints.
Right.
And so everybody was happy with 1.0, and why was there all of this
now it's another question. Now it's another question.
Yeah.
So sometimes there are actually cases in which you do want to pick different versions. Sometimes there's a private use of something, and you do want to make sure that you don't use a higher version. You want to use, say, I only tested my with specifically version 1.1.1. I know that anything else may break me. I really want conservative. I promise I will not expose anything of this in a public API, and please don't break me by giving me a better user experience. So I might import the same module and says, well, I actually don't care about details. I'm pretty good giving the latest and greatest because I want to pick up the newest features. It's actually a very valid use case. So we could do what you would suggest in some cases, but not in all of them anyway. So this is why the extra complexity is necessary in the system anyway, but maybe you're right that for some cases we could use a simpler system.
Well, and also the repository and things like that, they can be added and changed dynamically at runtime, right? So you cannot really just figure out the intersections at startup time and use that forever in the JVM sessions. Yeah.
Liz?
Well, given what you just said, where it might be right in one case to
Right.
pick like the sort of smallest, lowest common denominator, or it might be in one case not. It seems like it could be specified in the syntax of that attribute, so the module author could say, it's going to be better if we don't load 2 copies of this. So we're going to, to tell the repository system, work, as long as I get something in this range, I'm good to go. So do whatever you need to do to prevent two copies of the module being loaded.
So the suggestion is to have an extra bit on every import statement that says basically, I'm willing to take a lower version than the highest one that meets my constraints, if this will help you in sharing. I don't know the answer is. We have not considered this, I guess.
Yeah, we can probably just,
It's a very good point.
So can module dependencies be resolved sort of downward in the chain? So if there's a module in the Bootstrap repository, can that resolve an import against like the application repository?
No.
Let me put questions. Is it if there's an input in the higher repository, in the Bootstrap repository, for example, Bootstrap repository, can it be resolved from a lower repository? So yeah, the answer is no.
Yeah, the answer is no.
But the answer is no, and the reason is because of this trust model. You also assume that going down in the graph, that you trust repositories less. So you don't want this to happen just to make the model simple. So you don't want to, it might, what you suggest might work, but just to make it easy to reason about, you don't never allowed to resolve things down.
The reason I ask is that in sort of regular web applications, people tend to have this problem where like you put one thing at like one level of the class map, then you have to sort of push everything up there. And I was wondering if this would sort of give a way
No, so one could certainly imagine ways of doing this, but to make the security model simple and easy to understand, we just opted for a simple solution.
Yeah.
So there are a number of proposals. I can't think of the JSR numbers now, but for implementing inter-module protections, some degree of separation in the security sense between modules. How does the JSR 277 interact with these? Does it at all?
So the question is about some proposals that have to do with security in intermodule dependencies. Intermodule security. I'm not aware of this.
Do you know the JSR number?
There's 3. There's the deployment, there's the development, and there's OSGL.
No, but
I don't think this is what his point.
This is the protection domain model for different modules in JavaScript.
Are you talking about the isolation API or some? Yeah. Okay, we can probably take that offline.
So no, not exactly sure. So let's take it offline and
yeah.
Josh.
This is really a 294 question. Last time I looked at it, super package was 2 words, so you didn't have to introduce an extra keyword. Now it's even morphed, and member appears to have reared its ugly head as well.
Right.
So what's going on?
So this is a question about the 294 syntax, and the question is that earlier versions of the same syntax had super packaged as 2 words, basically using existing keywords of the Java language, and had no member keyword. And now there's those changes. There's a new keyword member, and there's a new single word super package. So there's an early strawman floated by Andreas and Alex maybe 4 weeks ago, and it has all the new changes. None of the experts that the 294 mailing list, which is public, which you can all see, hasn't really had a lot of deep discussions, mostly because of Java 1 coming up and many experts being busy with this. I can expect it's one of the issues that will be debated. I also have the same actually question, but I didn't want to raise it yet on the mailing list. So I don't have the answer. Do you have the answer?
No.
I absolutely agree.
Right.
I agree with it. I think there's both changes are unnecessary and don't bias anything. I agree with this.
Yep.
Can the resources exported by a module be specified outside of the source code?
The question is if the resources exported by a module can they be specified outside of the source code?
Yes, source code.
That's a good question.
Like a build system
Right.
might
Sure.
compile and generate some of the resources that might have multiple ways
Yeah.
of doing it.
Yeah,
So,
but I think as long as you package all these resources at the end, right, into Java as one unit, and deploy it that way, then we don't really care where the original resource came from.
Let me be more specific. So that those.
Generate a super package file.
Yeah.
Right. So there are 2 different JSRs. From the point of view of what we talked about today, the 277 JSR, it's completely irrelevant to us. We just want to get those files. One path of getting those files is by using the JavaScript compiler and what's specified in JSR 294. one might imagine that you actually write code in some other language, maybe in Python or whatever, and you compile it into Java bytecodes and use your own tools. And we don't care where those files come from. So from our point of view, what you say is totally possible. It could be some tools, wherever, that will make it possible. And it's, I think, a matter of tooling. Maybe there's a way to use JSR 294 compiler first, then add some things. Or it's not really part of this JSR. This is the answer.
So you made a comment that if you end up with 2 different versions of the same package and program somehow, cross them over, you get a class cast exception. I don't think that's right unless there's a cast in your code. I would expect a verifier error.
Right. So
I expected something of foo, and I got something of type foo, class loader, other over here.
Right. So this question is about cutting and imprecision, what I said earlier. So I said earlier that it's possible that if in my examples of modules A, B, C, and multiple versions of D, if B and C shared in the APIs module D, then there will be some class cast error. This is actually imprecise and incorrect. There are really 2 things that might happen. One is that at validation time, we would detect an error, and it will be not actually, there will be no exception raised as class exception. Or the other case might happen is that one of those modules, module B, for example, accepts something of type object, and then it expects that it's really some type of class D and does a cast, and then we runtime exception. So you're right. I was absolutely loose with my terminology. I want it to be compact.
So there's a related question, and I don't know if you can answer this, but when I'm compiling my application, am I supposed to compile one module at a time, or can I compile code across modules? And if I'm compiling code across modules, might the compiler have to see one version of foo over here and a different version of foo over here because they have different constraints?
Right. So the question is, what happens if I compile across different modules, and because there are different version constraints, I would see different versions? So the answer is that from the JSR 294 point of view, versioning doesn't really exist. So it is indeed, even without the complex cases that you specified, it's already possible that I compile against some version of module I depend on. And then later at deployment time, I get a newer version that happens to not have some class defined. It's already possible, right? I can see an incompatible version. And the fact that the Java compiler team doesn't really think that the version should be part of the language is kind of, I think, at the root of this problem. You can argue at a philosophical level whether it makes sense or not. But once we made the decision that the Java language and the Java compiler doesn't reason about versioning, you have all sorts of problems, including the one that you mentioned, and I don't have a good answer. This is more of a JSR 294 problem, right?
Okay. The consequence is the compile time resolution of the classes and the runtime resolution of classes are not the same thing.
Right. And it also goes back to the question about re-exports. There are many things that the compiler could be aware of, and the current proposal from the 294, it is not aware of, and there indeed could cause lots of problems.
We're going to enter version hell now.
Well, so the 294 deliberation just started. So we definitely have a way to impact the 294 proposal. So I would definitely if you have, please send email to me or directly to the spec leads, and we can definitely try to work on
Having a different resolution at compile and runtime in some cases is essential for versioning to work correctly. If you try to make them the same, then you really break things.
So all those things, by the way, were discussed at length in the expert groups of 2007, and there are there's no single uniform answer that everyone would agree on. So this is kind of why we are where we are.
I might be a little confused, but do you allow different versions of the same module loaded at the same time?
The question is whether we allow 2 different versions of the same modules to be loaded at the same time at runtime. The answer is yes. My slides about sharing was basically we're trying to say that it is usually the desirable thing to share the same version of module for performance reasons and to avoid those different kinds of class cast and resolution errors and validation errors that you may get. But in some cases, it is indeed what you want, and we will support this. You can have multiple copies of the same module.
Do you require modifications in the VM then once this JSR is approved?
So the question is, do we require modifications to the JVM? The answer is yes, but not for the reason that you mentioned the question before. Every module is loaded in its own class loader. So even if that class have the same name in 2 different modules, they're loaded at the same time because they all have their own class loaders. Today's JVM semantics already support this separation. So this is actually already solved by today's JVM semantics. But for other reasons, for enforcing information hiding, we will have some support in the JVM. Yeah. So I think that's it. Thank you very much for coming. Did you enjoy the talk?